This is a continuation of the notes on acids and bases. You should have already seen the first one. Acids and bases are very important classes of chemicals, or species of chemicals, as we say, and we will be learning more about them in these second notes. So far, we talked about that acids dissociate, which is like that. They break into ions. That doesn't mean they were ionic compounds necessarily to begin with, but the water molecules overpower them, ripping them apart, okay? And notice that what wound up forming was a chloride ion. Well, who cares about that? And a hydronium ion. Ooh, that's interesting. The hydronium ion, H3O positive on the top there, is a very important ion, and it causes lots of chemical reactions to ensue. Bases often do a similar thing. They dissociate into a sodium ion in this case, no big deal, and hydroxide, OH negative, which is a big deal. So the Arrhenius definitions that we've already covered are that an acid generates hydronium in solution, a base generates hydroxide in solution. Probably we're talking about aqueous solutions here. When you're not talking about aqueous solutions, this process becomes a little bit harder to visualize. But remember that hydronium and hydroxide are essentially opposites of each other. And acids and bases are generally considered opposites to each other. Hydronium has a positive charge, hydroxide has a negative charge. Hydronium is like water with an extra hydrogen. Hydroxide is like water missing a hydrogen. Well, what about water? Water is a very interesting chemical. Of course, it's incredibly ubiquitous and very, very polar. It's important in chemistry. It finds itself at the nexus of a lot of chemical understanding. Well, if you try to get water very, very pure, water has a dirty little secret. And now I finally must confess water's little secret to you. I've been trying to avoid this thus far in chemistry, but here it goes. Water can never, ever be pure. The reason water can never be pure is because water does something interesting. When water is left, let's say, all to itself, water will actually self-ionize. What that means is one water molecule will sometimes steal a hydrogen from its neighbor, another water molecule. Now this seems very unlikely. What? Aren't they equal? Aren't they the same? Yes, they're equal. Yes, they're the same. But depending on the way they collide, all kinds of little parameters, thermodynamics, every possible impact and collision that can occur, every once in a while, one will get the advantage over the other. The result of this is that two water molecules, after self-ionizing, will produce a hydronium ion and a hydroxide ion. So now think about this. Is water an acid or is water a base? Well, let's think about this. Water makes hydronium. It generates hydronium. I guess it's in solution. It's with other water. Isn't that an acid? Yes. But then again, didn't it just generate hydroxide also? So isn't water a base? Yes. Water is actually something, a class of chemicals that can be put in both categories. However, it can't fall in both categories at the same time. It has to be in one category or the other, kind of like an amphibian, a creature that lives on land or in the water. It can live in one or the other, one at a time though, right? It can be on land at one moment and then in the water at another moment. So the word for this that describes water is amphoteric. There are a class of chemicals called amphoteric chemicals, and they can sometimes act like an acid and sometimes act like a base. If they are left on their own, only water molecules, well then some of the water molecules will act like an acid and some of the water molecules will act like a base. If they are mixed with other chemicals, well then generally what they do is the opposite of whatever they're presented with. So let's say water is presented with an acid. Well, what's the opposite of an acid? A base. Water will act like a base. What if water is presented with a base? Well, water will probably act like, what's the opposite? An acid. What if water is presented with a metal? Well, that kind of depends. Is it a base metal, one of the everyday metals that reacts with acid, the ones above hydrogen on the activity series? Well, if it's a base metal, water will act like an acid. Or what if it's one of those fancy-dancy noble metals, the ones that don't react with acid? Well, guess what? Water will act like a base. So water is amphoteric, and there are a select few chemicals that fall in this category, and it can act like an acid or a base. So the dirty little secret is, even if you leave water alone, get everything else out of it as pure as it could possibly ever be, water does this to itself. It self-ionizes into hydronium and hydroxide. However, let me mention, most water molecules don't do this. Most of them are staying H2O. A very, very few are doing this. But that means that in any glass of water, any raindrop, any water you find anywhere, there's always going to be a little tiny bit of hydronium and hydroxide in the water. You can picture this happening by imagining a whole bunch of water molecules. Remember, these are very, very tiny little guys, and they wouldn't be this organized, of course, in a liquid. They would actually be a little bit less organized, but let's just neaten them out so it's very obvious. And then this happens. Notice that one water molecule, the one that's on the left side, just stole a hydrogen from its neighbor, the one on the right side. The one on the left has now picked up a proton, a hydrogen ion, and now it's H3O positive. What's that called again? Hydronium. And it's left behind from the previous water molecule an OH negative. What's that called again? Hydroxide. So this is what we call the self-ionization of water. It did it to itself. Nobody else did it, just water on its own. So you get a little bit of hydronium and a little bit of hydroxide generated in water naturally. And this is happening all the time in every glass of water, every drop of rain, any little pond, any little stream, any puddle, anywhere there's water. This is always, always happening. This is why water can never, ever be completely pure H2O. There is a relationship between the hydronium ion and the hydroxide ion present in an aqueous solution. Aqueous solutions are solutions with water as the solvent. And if you have, let's say, a neutral solution, or even distilled water is a good example of a neutral solution. Well, because water is doing it to itself, well, the only source of hydronium is water stealing a hydrogen from its neighbor, and that's going to, of course, leave behind a hydroxide. So for every single hydronium you make, you're going to also make a hydroxide. That means they will be in equal amounts, equal concentrations, equal numbers, let's just say for now. But if you add an acid, which of course generates its own hydronium, well, that's going to throw off the balance. So in an acidic solution, you have more hydronium than hydroxide. And then if you add a base, well, that's going to generate hydroxide. Well, that's going to throw off the balance as well. In a base solution, you will have more hydroxide than hydronium. So notice on this little diagram, in the middle they're balanced, and then in an acidic solution you have more hydronium, which is tilting the scales towards hydronium, and then in a basic solution or alkaline solution you have more hydroxide, okay, than hydronium, which is tilting the scales for hydroxide. If you look carefully, you can also see that the amount of the opposite chemical has decreased. We'll talk about that a little bit more later. Here are just a few other amphoteric compounds, compounds that can either generate hydronium or generate hydroxide in solution depending on what they are presented with. However, there is more than one way to define an acid and more than one way to define a base. There's some that we will not be dealing with, like the Lewis definition. We are going to include this one though, because sometimes you need something that's a little bit more flexible when you're defining acids and bases. Okay, for example, acids don't have to be in solution. Definitely not always in aqueous solution. Bases don't have to either. So how would you define them if they weren't really in solution? They could be in the form of a gas. That doesn't sound good. Having a cloud of acid gas coming toward you doesn't sound good, and it's not, but they can be. And so what's another way to define acids and bases that doesn't involve talking only about when they're in solution or in aqueous solutions specifically? Well, here we go. The Bronsted-Lowry definition. A lot of people just say Bronsted-Lowry. The Bronsted-Lowry definition is as follows. Acids are proton donors and bases are proton acceptors. So a donor is somebody who goes and they give to charity and they're really, really nice people. And acceptors are people that take things. Okay, but it isn't really so polite. The way this happens is much less polite than this would make it sound. Acids don't want to give their protons. Their protons are ripped away from them. They are torn off. And that is why they lose protons. Bases don't just accept protons, just get them in the mail like a UPS package. They actually grab them and pull them. So bases are proton takers is another way to say this. Acids are proton losers and bases are proton gainers. There's a bunch of different ways to say this. The donor-acceptor thing is a little euphemistic. It makes it sound like it's very passive, where it is not. It is a very active process. So this definition works. What if your acid is a powder? It's still a proton donor. What if your acid is a gas? It's still a proton donor. It might not necessarily generate hydronium in those situations, but it's still a proton donor, willing to lose its proton, easily losing its proton to anything surrounding it. So this definition is much more flexible, but if you think about it, it still kind of matches up with the other one, with the Arrhenius definition, because if you donate a proton, think about it, if you give away a proton in an aqueous solution, where is it going to wind up? It's going to wind up stuck to a water molecule, and isn't that going to make hydronium anyway? And if you accept a proton, what about take? That might be a better word. What if you take a proton from a water molecule? Aren't you going to generate hydroxide? In fact, that is another way that bases generate hydroxide, as you will soon see. So this is the Bronsted-Lowry definitions of acids and bases: proton donors and proton acceptors. Again, the Bronsted-Lowry definition: an acid is a proton donor, a base is a proton acceptor. Acids lose protons, bases gain protons. Protons are hydrogen ions. Don't forget, H+. Here's an example of what we like to call a Bronsted-Lowry base. NH3 is ammonia, a very common chemical. Well, ammonia is interesting because it's one of the very, very few chemicals that can beat water in a fight. What I mean by that is, well, water is a very polar molecule. It has an extremely polar bond between the oxygen and the hydrogen. And it has two of them. So it's like double polar. But then again, nitrogen and hydrogen, they also have a polar bond. Well, it's not quite as strong as the one between hydrogen and oxygen, but it's still pretty good. And wait, it's got three of them. And so it's kind of like triple polar. These are not proper chemical terms, by the way. So that means if it comes to a battle and it was water versus ammonia, well, ammonia is going to win. And so what ammonia will do is steal a hydrogen from a water molecule. This will generate, do you remember what that's called? NH4 positive? We've seen it before. Ammonium. Ammonium. Ammonium is a positively charged cation that forms when ammonia steals a hydrogen from a water molecule. So what's left behind? Hydroxide. So isn't that a base? Yes. Why? Because it's a proton acceptor. So it's a Bronsted-Lowry base. But didn't it also generate hydroxide, just like in the Arrhenius definition? Yes, it did. So this is what we call a Bronsted-Lowry base, ammonia. It took a hydrogen from a water molecule and it generated hydroxide a different way. By the way, not every single ammonia will steal a hydrogen from every single water molecule. Just statistically, it's going to happen because ammonia has a slight edge over water. I don't want to make it sound like it's a knockout fight. It's a slim margin. So ammonia, if you put it in aqueous solution, like the cleaner ammonia that a lot of people use to clean with, it's kind of smells bad, but if you don't mind that, it's a pretty good cleaner. Inside that ammonia solution, well, there's always ammonium. There's got to be, because look at what happens. Ammonia forms ammonium when it steals a hydrogen from the surrounding water. So it is a base. The Bronsted-Lowry definition gives rise to the concept of conjugates, that for every acid, like hydrochloric acid, there is a conjugate base, which is sort of like what's left after the acid has donated its proton. What's left after HCl loses its H? Chloride. That is the conjugate base. So that is a pair of conjugates. Hydrochloric acid and chloride ion are a conjugate pair. Now in this situation, oh look, we've got water. Well, water is being presented with an acid. So what do you think water is going to act like? Water is going to act like a base. And if water is acting like a base, well then its conjugate is going to have to be an acid. So this is another conjugate pair. Water is a base in this situation, and hydronium, of course, is an acid. It's the real acid. So acids and bases under the Bronsted-Lowry definition are identified based on whether they donate or accept hydrogen ions, which are, of course, the same thing as protons. So any conjugate base is the same as the starting acid minus the H+. Like take an H+ off of it, and what you're left with is the base. That's why a lot of bases are anions, a lot of conjugate bases are anions with a negative charge because you've taken away an H+. The Bronsted-Lowry definition gives rise to the concept of conjugates. For every acid, there is a conjugate base. For every base, there is a conjugate acid. The difference between the two of them is always an H+, a hydrogen ion, a proton. On this table, which is found in your book in chapter 15, you will see a list of acids on the left. and a list of their conjugate bases on the right. For example, the very first one is hydrochloric acid, HCl. Take away an H plus from that, and what you're left with is a chloride ion, Cl minus. Go down a couple to hydronium. You'll see the hydronium ion, H3O positive, which of course is the real acid. Take away an H plus from that, and what you're left with is water, which is a conjugate base. Remember, water is amphoteric, so it can act as either one. If you read the table from the bottom up, however, look at the bottom where it says base on the right. Well, if you start off with a base, like, oh yeah, go up to, let's say, hydroxide, the one at the very bottom, and add an H plus to that, and you've got the conjugate acid. The conjugate acid for hydroxide is water. So water finds itself on both sides because it's amphoteric. A better example would be on the base side, on the right side, go up 3 to ammonia, NH3. Well, add an H plus to that, and you've got NH4 positive, ammonium. So every acid has a conjugate base, every base has a conjugate acid, and then the strength of the acid is inversely related to the strength of the conjugate base, and vice versa. For example, if hydrochloric acid is a really strong acid, and it really wants to donate that proton, well then the chloride ion really isn't going to be grabbing that proton back, isn't going to be accepting that proton back. So in other words, the strength of the acid is inversely related to the strength of its conjugate base, and the strength of the base, for the same reason, is inversely related to the strength of the conjugate acid. So if it's a strong base, it's going to have a weak conjugate acid. If it's a weak base, it's going to have a strong conjugate acid. And if it's moderate, well, it'll probably be like moderate in both categories. Here's a little table showing some strong acids and some weak acids. Well, strong acids like hydrochloric acid, well, we like to use that one in the lab all the time. That's the one we like to use to understand acids as well. Nitric acid, well, we don't use that indoors, but we do use that in some of our demos. That is a nasty customer. And sulfuric acid, which I likened to the drool of the alien from the movie Alien, the Ridley Scott movie, is kind of a nasty customer as well. So the ones on the left are generally considered the really hazardous acids. And on the right, we see the weaker acids. Well, acetic acid actually can be written more than one way. The way you see it written here is not my favorite way. This is the way organic chemists prefer to write it. Okay? And then we've got another one down in the middle. We've got hydrofluoric acid. Well, it says here that hydrofluoric acid is a weak acid. However, that is not one that you want to have around your body, because hydrofluoric acid is an acid that will react strongly with organic materials. Oh yeah, that's what we're made of, organic materials. So what makes an acid strong, or what makes an acid weak? Well, let's look at some hydrochloric acid in water. Again, pretend those water molecules are a little less organized, that it would be a liquid. What happens when you put HCl into water? Well, this happens. It dissociates. So if an acid dissociates, if it fully dissociates, if every single one of them is ripped apart by the water molecules, you will get a lot of hydronium. And it turns out hydronium is what does all the work that acids get credit for. It's the real workhorse for the acid. It's the true acid. On the other hand, what if only some of them dissociated? If only half of your molecules actually dissociate, well then you're only going to get half as much hydronium as you have molecules. Well, that's going to be a lot weaker. So what if only 10% dissociate? That's going to be even weaker still. What if only 1% dissociate, or 0.1%? And we find all those things with acids. Sometimes only a very, very small number of them, percentage of them, will dissociate. Those are the weaker acids. So the strength of an acid depends on dissociation. The ones that don't dissociate are weak acids. Well, we've been using hydrochloric acid as our example, maybe a little too much here. Because which is it? Is it a strong acid or a weak acid? Well, I don't want to reveal that yet. You will see that in a later lab. However, just keep in mind any acid is really a hydrogen ion stuck to its conjugate base. So when it rips off, like so, what you are left with is often an anion, which is the conjugate base of that acid. So for any acid, not just HCl, but any acid, what it's going to leave behind is hydronium for sure, and some kind of conjugate base, depending on what the anion was in the acid. If it's a weak acid, well, same thing. Only a portion of them are going to dissociate, and you'll be left with the conjugate base and hydronium. Again, however, notice that the one on the right is still intact. It's still an intact molecule. It has not dissociated. So that is what makes this a weak acid, if not all of them dissociate. The more that remain together, the weaker the acid is. But doesn't that make that a strong molecule? So really, if the molecule is stronger, it makes a weak acid interesting. This gives rise to what, it's almost like a Zen saying. I have Yoda saying here, an acid's very weakness becomes its strength. For the more it dissociates, the more hydronium is generated. I probably should have had him saying it backwards, but that might have been more confusing. I guess Yoda kind of says things backwards. Oh well. So in other words, an acid's very weakness becomes its strength. What I mean by that is if the molecule is very fragile, very weakly held together, so much so that if it's put into water, water can rip it apart, dissociate it, well, that's what makes a strong acid. So a weak molecule makes a strong acid. The more it dissociates, the more hydronium is generated. The opposite of what this says here is what if you have a very strong molecule? Well, then water is not going to be able to really rip it apart, is it? And if it can't dissociate it, if it can't rip it apart, well, then it won't make ions, it won't make hydronium, and that's a weak acid. So a strong molecule, ironically, makes a very weak acid. And a weak molecule, compared to water, I mean, water is pretty tough, but if you're weaker than water, let's say, well, that's going to make you a strong acid. There is another factor to consider when you're talking about how strong an acid is, and that is whether it is a monoprotic acid or a diprotic acid. A monoprotic acid only has one hydrogen to give. It dissociates and winds up making one hydronium. But a diprotic acid will give away two hydrogen, and if you give away two hydrogen ions, well, then you make two hydronium. That's double the hydronium. For every molecule of a diprotic acid, you wind up making two ions of hydronium. So if you have 1 mole of that acid, it could potentially make up to 2 moles of hydronium. And then, as you can imagine, there's triprotic acids and so on. But for the most part, we're going to be talking about monoprotic and diprotic. Well, this is another factor to consider, and this will show up on one of our labs, or maybe more than one of our future labs. So those were the second notes on acids and bases. We've added another definition. So now we've got 2 definitions for acids and bases. We've learned about water and its properties, its amphoteric properties. And we've begun to talk about what makes an acid strong or weak. We will continue in the next notes. Again, we will be getting quantitative soon.